Today we're going to talk about how we produce the names for ionic compounds. So everything in chemistry has a systematic method for coming up with a unique name for every compound. This system is devised by what's known as the International Union for Pure and Applied Chemistry, often referred to as IUPAC for short, for its acronym IUPAC. And everything needs to kind of follow these rules. So it's important that we're able to name the things that we're talking about, is especially once we get into more complex formulas. Speaking the formulas is cumbersome and often unclear, but being able to produce the unique name for the exact compound we're talking about is going to be really useful to us. So for ionic compounds, it's pretty straightforward. We write the name of the cation followed by the name of the anion. So for monatomic cations, that means for just one atom of one element, that's a cation. The name of the ion is exactly the same as the name of the element. So for example, Na plus is just called the sodium ion. So in our name, it's just going to say sodium. Ca2 plus is calcium ion. So nothing in our name actually changes. For monatomic anions, it's a little bit different. The ending of whatever the element name is going to change to ide, to IDE. So, for example, the ion formed by chlorine is Cl minus, and we refer to that as the chloride ion. So chlorine, INE, that ending of ene gets replaced with ide. O2 minus, the oxygen, the ion formed by oxygen, is known as the oxide ion. So this one we're actually replacing most of the word. The igen is replaced with ide, with IDE. So exactly what you replace is basically whatever sounds normal, and you get a feel for that as you go along. Don't stress about it too much, as long as you're kind of getting the point across that you're replacing some part of the element name with ide. That's fine for now. But if you think about, with oxygen, do I replace just the N? If you replace just the last syllable here, you get oxyide, which sounds really weird. So try and figure out just what sounds good. If you have questions about specific elements, you're always welcome to ask me. And then for polyatomic ions, you just use the name of the polyatomic ion as it's given to you on your list. So for simple compounds that only involve monatomic ions, naming is pretty straightforward. Name the cation, name the anion, done. So NaCl, we've already seen the name of this sodium ion is sodium ion. The name of the ion formed by chlorine is the chloride ion. So NaCl, the official name for that is sodium chloride. So we just name the cation, name the anion, done. And it always goes in that order, cation first, followed by anion. If we wanted to do BAS. So our cation is barium. Our anion is sulfur, and that's going to become sulfide. So this will be barium sulfide. If we have this guy, our cation is calcium. Our anion is a polyatomic. If you look on your list, you'll find that that's the formula for acetate. So that's the name of our anion. So this is calcium acetate. So I'm going to give you two more examples to pause the video and try on your own. So why don't you do KF and SrNO3, 2. So pause the video here and try to name these two compounds based on what we just talked about. So the first one here, K, is potassium. And for the cation, the element name doesn't change at all. Then our anion is the ion of fluorine. Our ene is going to change to ide since it's an anion. So this is potassium fluoride. And then for the second one, our cation is strontium. And our anion is a polyatomic. You can look on your list and find that that's called nitrate. So when you have most cations and anions, things are pretty straightforward. We don't need to specify anything about how many ions there are, because each, as we said in the previous video, each pair of ions can only combine one way. So sodium chloride always contains one sodium and one chloride, because that is the only way that their charges can add up to 0. Calcium acetate always contains one calcium and two acetates, because that's how their charges can add up to 0. So the only time things get a little bit weird is when you have an element that can form more than one possible charge. So we said yesterday that this applied to that whole region in the middle, what we call the transition metals. So that's the sort of center chunk of the periodic table, center section. And tin and lead also. Most of that group, so tin and lead were in the carbon family, and I said most of that group doesn't typically form ions, but tin and lead do, and they can be either +2 or +4. And most of the transition metals also have multiple options for what charge they can form. So when that's the case, we need to specify which charge our ion has. So we do that in chemistry in names using Roman numerals. We'll put a Roman numeral in parentheses after the ion name. So if we're writing a name from a formula, let's do Fe2O3. Actually, let's do a simpler one first. We'll get to that one. Let's do FeO. So in order to specify the charge, we need to know what the charge is. So iron has options, either +2 or +3. You don't specifically need to know that. But oxygen doesn't. Oxygen and everything in its family tends to form ions with a -2 charge. So if this is a formula that exists, and I'm telling you that it is, that means that in this compound, iron must have a +2 charge in order for the overall charge to be 0, and that will always be true. If oxygen is -2, in this 1-to-1 ratio, iron must be +2. So when we write the name for this, it's going to be effectively the same, but we're sticking something else in the middle. So we still have iron oxide, but there are 2 different iron oxides, and we need to specify which one we're talking about. So we do that by putting a Roman numeral after the cation name with the charge. So note that this corresponds to the charge on your ion. A lot of people get confused and think it's how many atoms there are, but that is incorrect. It's telling you that this iron has a +2 charge in this particular compound where it's paired with oxygen. So if we look at Fe2O3, oxygen still always has a -2 charge, but now we have 3 of them. So there's a grand total of 6 negative charges here. we don't know what the charge on iron is, but 2 of them has to equal +6 in order to balance this out. So that means that the iron in this situation must be +3 in order for this compound to work. So this one would be iron 3 oxide. So again, we're specifying the charge on our cation using this Roman numeral. And it's only cations that can form multiple charges, so your Roman numeral will only ever need to go after the cation. So I'm going to put a couple more examples for you to pause the video and try on your own. So let's do Cu2S, let's do PbNO3 2, and one more. Let's do sure, CrO. Nah, let's not do that one. Keep giving you things all in the same family. Let's do OSCl8. So pause here, try and name those 3 compounds, and then we'll do them together. So in the first one, again, once we recognize that this is an ion that can have multiple charges, we need to figure out which charge is present in this compound. So copper is a transition metal, it's in the middle portion of the periodic table. Sulfur is in the same family as oxygen, so this likes to have a -2 charge. Means that all of my coppers together need to total +2, and whatever the charge is, there are 2 of them. So each one must be +1. So the name for this compound is going to be copper 1 sulfide. So our charge was +1, so we have Roman numeral 1 after the copper. So in the next one, nitrate is a polyatomic ion, and that whole thing has a charge of -1, and there are 2 of them in this formula. So in total we have 2 negative charges, means that we need to have 2 positive charges to balance it out. There's only 1 lead ion here, so it must have a +2 charge. So this would be lead 2 nitrate. Charge of +2 becomes Roman numeral 2. And then last but not least, we have chlorine, and its family likes to form charges of -1. There are 8 of them in this formula, so that gives us a total of -8, which means that our osmium must have a charge of +8. So this will be osmium 8 chloride.